turn it over to Richard. And thank you guys.
Thank you.
So, evening everybody. I'm Richard Kreuter from NGen. I want to say thanks to Nick from UShip and UShip organizationally for hosting tonight and having us here. Here with my colleague Yarek, also from NGen. So I've been at NGen for about 22 months, so let's say 2 years, rounding up, and have seen a lot of customers over that time, customers, users of MongoDB, clients, whatever word you want to use, people who are using MongoDB. And that's informed a certain amount of experience in my head anyway of what people are doing with the system, what's good to do with the system, what's less good to do with the system, who's already using MongoDB in some capacity. I'm willing to admit it. All right, about half the room. I mean, I say willing to admit it not because you'd be embarrassed, but because for some people MongoDB is a secret weapon. Right? So the point of this, or the structure of this talk, is actual sort of experiential patterns of what I see people doing in different spaces without naming any names. So if you're in one of the spaces that I'm about to describe, this might be relevant to you. If you're not in one of the spaces that I'm about to describe, the functionality of MongoDB that I'm going to cover might nevertheless be relevant to you. So the reason that I have this slightly funny topic, patterns and anti-patterns, is primarily that I've been around MongoDB long enough, and I've been giving talks and presentations and trainings and so forth and consulting on MongoDB long enough that I feel like a lot of people pretty much know the basics. So I'm hoping that you're not here for an intro to MongoDB talk. There are many, many fine decks of slides online if you're looking for an intro to MongoDB talk, and also videos as well. So I'm not trying to scare you away if you're looking for an introductory talk, but this may be a little bit less of an introductory talk. Okay, so what's the big picture? MongoDB, we claim, is designed for helping you work with large volumes of highly volatile, complicated data. So you might have a huge amount of data that is relatively simple in structure, or you might have a small amount of data that is fairly complicated in structure, or somewhere in between. And you might be writing it at a very high rate, or it might be that you're inserting lots of documents, but once those documents are inserted, you don't change them very much, maybe for various kinds of reasons. Now, lots of systems can do something like this, either high volume or large volume or high volatility or complicated or whatever, some combination. I apologize for the people that are sitting over here. I can't quite be translucent. The point is that when you have data like this, whether you're using MongoDB or any other system, there are a number of things that you should think about that actually many of them have very little to do with MongoDB, but the main point is you can probably do lots of things with this data, but it might take a while. So when you're talking about having 500 gigabytes of data or a few terabytes of data, certain things that sound conceptually simple, some of which I'm not actually going to address tonight, like making a backup or copying it somewhere, become decreasingly practical for reasons of time and space and cost. And so often you want to think, especially when you're designing your application, this talk will mostly focus on application design type things, rather than, there are a few operational type things that I mentioned at the end, but mostly I'm going to be talking about thinking about designing an application. When you're designing an application, you should think about, well, okay, maybe this works when I have no data, or very little data in the system because you're making a prototype, but is it going to work when you have a large deployment? So, what are some types of applications that we see a lot of? So there are, well, 4 relatively narrowly defined things, and then one thing that isn't actually tied to an application type, but I see a lot of logging or monitoring or event tracking type systems. So sensor data or host intrusion monitoring, network traffic monitoring, or logging of I don't know, gameplay events, that sort of thing. These sorts of applications tend to have high insert volumes and sometimes analytic requirements as well, often analytic requirements as well. So they might be inserting lots of events into the database and then be interested in sort of figuring out stuff about patterns after the fact. I oddly enough see a lot of, I mean, we at 10gen, when helping people use MongoDB, we see a lot of people who are doing something with ad networks. By the way, if you're in any of these first 4 bullet points, it might be a crowded space. So just, the fact that we're seeing a lot of it and we're, relatively small newcomer in the data storage space might mean that there are a lot more people doing it out there than might be expected. Anyway, I see a lot of people doing ad network impression decision-making systems that use MongoDB. And these have a few peculiarities. The problem, and I'll get back to these in more detail, but the problem that needs to be solved there has an interesting kind of peculiarity, which I'll get to in a moment. We see a lot of product metadata catalogs for e-commerce type sites. People who are selling things and need to store metadata about what they're selling. Now that's conceptually distinct from maybe inventory type systems, where they need to know how many of them they have on hand. We see a lot of people doing that with MongoDB too, but that's not as interesting from the point of view of what kinds of mistakes you can make or what kinds of sort of good features you could take advantage of. See a lot of things that amount to being social networks. So users of a system who have friends or followers or something else, people that they're related to, and information needs to be propagated around among graphs of relationships in these systems. And that's a very high level or abstract way of putting it, but you can imagine lots of different kinds of systems like this. One user who was implementing such a thing consistently referred to his own product as a Twitter clone. And then another sort of space, which is not strictly a kind of application, but is more of an architectural property that we're increasingly seeing people use MongoDB for, are some kind of service-oriented architectures where there are lots of distinct modules, each conceptually independent of the other, of all the others, implementing some business logic, talking to MongoDB, and there are some potentially interesting aspects of architectures like that that are sort of orthogonal to any particular application space, but that may influence some decision making about how you use MongoDB. So now I'm going to actually talk about patterns and anti-patterns. So if you're an event tracking system, a monitoring system, a logging system, stock tick data, something like that, one of the most common things that these systems are for is for some sort of analytic purpose. It's not that interesting to record lots of events unless you're doing something to analyze them. And a pattern that is pretty common and pretty powerful, and this is also not particularly MongoDB specific, although people tend not to have thought of it before they use MongoDB, is to actually effectively pre-compute whatever aggregates might need to be tracked. This is probably pretty obvious if you spent a lot of time in a monitoring system, like implementing some sort of monitoring or logging for analysis, or analytics for a logging system. But you want to have your data, conceptually speaking, denormalized in such a way that when new events come in, even if you're logging each individual event to one collection, as at this time this user did this, if you're counting things like how many times in a day any user did this, you probably want to have some other kind of broken out description of those counters. Why would you want this? Well, because at the moment, at any rate, MongoDB has some facilities for aggregation, such as counting and MapReduce and so forth, but they're not really that fast. And this is, arguably speaking, a flaw in MongoDB, but on the other hand, for many kinds of statistics where you can pre-compute the results as the data is coming in, computing it once and having that stuff be stored in a document that is structured according to the different kinds of roll-ups that you want to do is always going to beat dynamically computing something like this with something like a MapReduce job. Now, in future, we're planning on improving our aggregation functionality by means of a new aggregation facility about which I'm allowed to tell you nothing. But for the moment, and even for the rest of time, this should just be a moderately obvious fact. If you have to compute something, if you can compute something once and show the result over and over again, that's always going to beat computing it repeatedly anytime somebody asks the question. So what's an example of this sort of thing? Well, actually, this example in whatever that's Courier New, I think, in the middle of the screen is an example that's roughly based on our Mongo monitoring system's way of representing data. We have a monitoring system called the Mongo monitoring system. It's a freely available product. I'll mention it again later in case you don't get this pitch the first time. And it stores metrics on MongoDB deployments. And the metrics are broken out into basically documents by day with every granularity of counter as a separate field. And I didn't write the whole thing in because the whole thing would require, are there 1440 minutes in the day? I'm very bad at arithmetic. I think that's about right. Plus 24 hours, plus a daily counter, so 1440 plus 24 is 1460, so there would have to be 1465 counters in this thing that would fill up the screen. The point is, every time a statistic comes in, that statistic is added to the relevant field in the minute array, which would be an array of 1440 object. 1 second, please. It would be added to the hourly counter for the current hour, and it's added to the daily counter for the current day. The documents that are inserted into MongoDB are inserted in their initial state with a bunch of zeros, so that they're all padded out. The space for them is pre-allocated. In effect. Oh, he ran away. The guy that raised his hand. Oh, he's back. So the actual cost of doing this stuff in terms of how much data needs to be allocated is all sort of predictable and stable. The counters can be incremented all in place, and it's a rather efficient way of doing things. As I said, this might be obvious to people who are in this kind of space, but it might be non-obvious to people who are doing this who are new to doing this kind of thing. Now, not every problem in analytics can be handled this way, but many problems actually can. And whether or not it's obvious, computing something like a daily counter, keeping a daily counter up to date all the time is always going to be adding up the 1440 values that would be the broken out minutes, whatever way you slice it. I'm sorry, you had your hand up? You didn't? Didn't somebody have their hand up? Okay, good, thank you. All right, so that's what I claim is a pattern. Another kind of pattern that's common to event logging type, monitoring type applications is a need to age out old data. And there are a couple of different ways of doing this. On the one hand, if you store all of your data for some particular event stream in a single collection, presumably with some sort of timestamp field incorporated into your documents, you could periodically clean out documents that are older than some retention date. So if you're supposed to retain data for a week, then every so often you run a job that says delete everything that's older than however many seconds there are in a week or something like that, some timestamp. Now, there are better and worse ways of doing this. Probably the least good way of doing this is to stage those jobs to happen at exactly the same time and to do a whole sort of increment's worth, a very large increment of cleanup. So for example, if your retention policy is you want to keep things for 7 days, you could in principle at midnight on each day, try to delete everything that is more than 7 days old at that moment. So each day you'd be deleting about a day's worth of data. Now if a day's worth of data is very little, that may not matter. If a day's worth of data is a lot, you're basically focusing all of that cleanup load at a single moment in time. And so for the duration of that cleanup job, your system will be, it'll be performing extra work, right? So if your normal operational capacity, if your application, your overall system uses, let's say, 80% of the operational capacity of your MongoDB deployment, in principle, you could imagine such a cleanup job that's staged at a fixed point to do all of this work might push your system over capacity. By pushing your system over capacity, I just mean things get slow, possibly unacceptably slow. So a slightly better solution than that would be to stage cleanups of this sort in such a way that you disperse them throughout the day. Maybe every 5 minutes, try to clean up 5 minutes worth of data. That is to say, 5 minutes worth of data that is older than your retention policy. Provided that each such 5-minute cleanup takes less than 5 minutes, you're ahead of the game. And the other point to note about retention policy type, or aging out old data, is that even if you lag behind, that is, let's say your load suddenly increases because you've gained some new customers whose data you're logging. Even if you lag behind on the cleanup, you're probably not doing anything wrong with respect to what you're supposed to be providing to your customers. You're just holding on to extra data. So if you had to, for example, periodically or occasionally turn off your cleanup job, because you're suddenly under new load and you need to slow down the cleanup jobs or disable the cleanup jobs until you can add more capacity to your database, that's probably not going to break anything with respect to business requirements. But a slightly better way of doing an age out or a cleanup than either batch or sort of small batch incremental cleanups with removes dispersed throughout the day might be to allocate different collections or even different databases to represent time buckets. If you have a problem, if you have a situation where you only need to hold on to your data for, say, a week, you might allocate a new collection each week and start populating that new collection at the beginning of the week, because it's going to be more efficient to clean up a whole collection, to drop a whole collection, than it would be to remove, millions or tens of millions of documents from an individual collection. Just because of, basically because each document removal requires freeing up some space for that document, fixing up any index entries that might point to that document, to no longer point to that document, to record an entry in the replication oplog for the purposes of replicating secondaries. So there's a lot more work that has to go on to clean up 10 million documents than there is to just free up a collection containing 10 million documents. So that's another possible design strategy, is to bucket your data according to your retention policies, and then drop the buckets as you need. Now, we plan for MongoDB 2.2, which is scheduled for release early next year, to have a built-in feature which we're calling TTL collections, time-based collections, where you would define for this collection, given a certain field, and that field ought to be a timestamp, and a certain duration. So you specify what field to pay attention to and what duration to care about, and we'll automatically clean out documents that have that field if that field is older than some duration. And we'll do this, in the background periodically, so you wouldn't have to write your own job to do that. But nonetheless, you might still want to do this sort of thing in an application layer rather than in a database, because you might have finer grained control over, enabling or disabling the cleanup job, rate limiting it, or throttling the speed at which the cleanup job is getting run, and so forth. And of course, there might be other kinds of business requirements that might make things more complicated than a purely time-based retention policy. Is this much clearer? Is there anybody who's going to? If you feel like it, you can just raise your hand, and if I'm able to, I'll call on you. If I'm in the middle of a sentence, I might need to finish the sentence first. Okay, good. All right. So, what about an anti-pattern for event logging? So, if you're sharding an event log collection, which is not an unusual thing to want to do if you're logging lots of information, you don't want to pick you don't want to use a timestamp, a straight timestamp, as your shard key. So for people who are not yet familiar with MongoDB sharding architecture, our sharding architecture is designed to distribute your data around some number of ideally equally sized MongoDB sub-deployments. Each one would be a replica set, so each one would have copies of data within itself, and your data is intended to be balanced around. The volume of data is intended to be balanced around. But the data is balanced by ranges on a field that you specify called the shard key. Now, if you have any kind of monotonically increasing shard key, such as a timestamp, then there's exactly one range into which any new document is going to go. Specifically, the range that goes from some point up to, theoretically anyway, positive infinity. Right? So if you imagine a bunch of mathematical ranges over some domain, there's data that's older, and that lives over here. And then the newest data is going to actually all be in whatever is the maximum range. And our ranges, as I say, are sort of quasi-mathematical in the sense that they go from some point up to some other point, and there's going to be one range that goes up to positive infinity, so to speak. If your shard key is monotonically increasing, like a timestamp, and this applies just as well to an auto-incrementing serial number if you're doing something that involves auto-incrementing serial numbers, if you pick that as a shard key, then at the current point in time, or at the current serial number value, the next insertion will go into that range that goes from some point up to positive infinity. And then the next document will go into the same range, and then the next document will go into the same range. Eventually, that range will be split into some range that goes from one point to another, and then from the other point up to positive infinity. Nonetheless, all your inserts are always going to be going into some maximum topmost range, which means that if your write operations are insert heavy, if you're doing, let's say you're doing 100% inserts, because maybe you're just logging events, in that case you'd have a bottlenecking problem, because all your inserts would be going to the same shard at any particular point in time. Which shard they go to might move around from time to time, because there's some notion of migration of chunks of ranges from one shard to another. But at any particular point in time, all your writes are going to be pointing to the same shard. So basically, don't shard on that. Now, again, I put a lot of caveats there. That's if you're 100% write heavy. which a logging type system probably would be. If you were update heavy with fewer inserts, a monotonically increasing shard key like a timestamp might not be so bad. But many types of applications like this actually want to use a compound shard key, and the decision then becomes, what are you interested in querying on the most? If you're interested in querying based primarily on where the data is coming from, let's say you're logging users and timestamps. If you're interested in seeing what individual users do over durations, you would select a compound shard key. I suppose actually this bottom bullet point is a pattern, not an anti-pattern. You would pick a shard key that starts with the user, or if it's not a user, it could be a host, or if it's not a host, it could be whatever objects in your application space are generating the events, the interesting things that you're tracking, followed by a timestamp. Otherwise, if you're interested in seeing what all of your systems or all of your users are doing over time windows, you would start by something that's coarsely related to the timestamp, like perhaps the day, or the current timestamp modulo 86,400 seconds in the day, something like that. So that you would have something that's coarsely monotonically increasing, followed by the data source, assuming that the data source, like the user or the host or something like that, was reasonably randomly distributed throughout that domain. That sort of shard key has a pretty good distribution pattern and will allow your writes to be distributed around. And one or the other of those will support one or the other kind of query. So if you're interested primarily in querying based on time windows, you would pick a coarsely increasing timestamp followed by the data source. If you're interested primarily in analyzing by the where the data came from, you would pick a data source followed by something like a timestamp. So far, so good?
This is probably obvious, but if you've got your data sharded, querying, you ideally want all your queries to execute on the fewest number of shards.
Yes. Yes. So the question was, if you have your data sharded, your goal is to have the queries be executed in the smallest number of shards that it can. The answer is yes, and that's why you have to think about whether your application's query pattern for data like this would be primarily based on time windows or primarily based on data sources for the postulated kind of application. Shard key selection is actually something that requires a fair bit of thought. Okay, now let's talk about something like ad networks. Now I should say about ad networks that for people who know sort of the prehistory of MongoDB, you might find this to be an entertaining story. Our two founders, Dwight Merriman and Elliot Horowitz, got to know each other, I think, at least anyway, and worked together at DoubleClick. Dwight was a co-founder of DoubleClick, and Elliot was, I think, they were senior scientist. And and of course, DoubleClick, is the ad service network. And starting with DoubleClick and then following on through a number of intervening startups, they did a lot of work that more or less inspired the design of MongoDB based on their experience with the requirements of high-performance data stores. One of the sort of principal things that we see people doing, that I see people doing with MongoDB for the purpose of ad service, is trying to store what users of the system, whatever the ad network is targeting, should see what ads. They need to support that decision process. And generally speaking, there are requirements like don't show a user an ad they've already seen before, that sort of thing, or maybe an ad that they've already clicked on. But in general, if you have 10 million users and, I don't know, 100,000 ads, the total possible space of who's seen what is the product of the number of users times the number of ads. It's a pretty big space. It's a lot of data if you were to try to denormalize it that way. And additionally, of course, the spaces of users and ads are not static. Ads are constantly being rotated in and out of circulation or priority or whatever. There are lots of interesting sorts of business requirements here. And so the simple approach is to just store for each user, and it doesn't, to a certain extent, it doesn't matter how you store this information, but the simple approach is to store for each user what ads they've already seen, since the typical user will only have seen a very small subset of the ads that are available. I might have seen 500 ads that are currently valid out of the 10,000 that might currently be valid. The trouble is, when you actually try to use that information to figure out what to show me next, the naive or the simple thing that you might expect to do is say, well, okay, I know which 500 ads Richard has seen, so all I have to do now is find one ad that he hasn't seen. MongoDB has a query operator for this. It's called $NIN. For people who aren't familiar with MongoDB and its query language, don't worry about it. That just means not in if you're fluent in SQL. The trouble is, that's not a really good way to do things, because presumably there are lots of other constraints that are also being applied to ads, and so, don't show me things that are not interesting to me. I'm not personally interested in skiing or something like that, so there might be lots of other profile information that you have around me. So tacking on something like a $not in query, saying, I want some ads that have a lot of criteria, oh, and they're also not any of these 500, is going to be a very expensive operation, or comparatively a fairly expensive operation for any individual user. And if you're trying to do this concurrently for thousands of users in the same second, the performance is going to get pretty bad pretty quickly. So what I would suggest for these sorts of systems, and what we've generally kind of recommended that people do, is describe in the next slide. So rather than every time somebody wants to see an ad, figure out one ad they haven't seen, use the fact that at any particular moment, for a short duration, the ads that I haven't seen at this minute are likely to remain ads that I haven't seen for several more minutes. Basically, to use the results of one such query as a cache for subsequent such queries. So basically, when I visit some site and you're supposed to decide what ads to serve me, rather than pulling just one of them and saying, okay, you haven't seen this one, and then writing back that I haven't seen it, or that I have seen it, pull out 500, or whatever your business requirements permit, some number, or just some sort of bucket based on timestamps or something like that, and cache that somewhere. And then hit that cache, rather than doing this not inquiry every single time you're trying to decide whether to serve me or anybody else an ad. Now, again, this will vary a bit from requirement to requirement. You can imagine that some sites, or some, I should say, ad networks, have much more complicated rules than just allowing you to cache this sort of thing. But you might be able to do this, even if you can't cache things based on time, you might be able to run sort of a background job saying, okay, who's logged in the last day, and pre-populate as frequently as you can, or as quickly as you can, however well your database deployment will allow you, some cache of results that you can start out with. This is, again, not technically MongoDB specific. It just so happens that we see a lot of people doing this with MongoDB because our data structures provide a lot of flexibility for storing certain sorts of things, like what ads I have seen or what ads I haven't seen, in a very efficient to access sort of way. The trouble is, getting to what ads I haven't seen from what ads I have seen is never going to be efficient just because of the combinatorics of the problem. Question?
People that are doing this really well, are they also people that usually do it very well? Are they also using MongoDB for the cache, or are they using some other cache uses? Yeah.
So the question was, are people using MongoDB for the cache that I'm proposing that you might use for these sorts of problems? And the answer is, yeah, we recommend that. To a pretty good approximation, MongoDB architecturally ends up acting a lot like a persistent memory cache once it's been warmed up and running for a while. That is to say, we use memory mapped files in a fairly direct way. So our data files on disk, we just page them in, or we just ask the operating system to memory map them, and they get paged in as we access them. And there's very little transformation internally of data that's being served to you or data that's being inserted in the server between what you send over the wire. That's actually stored pretty much verbatim on disk. And so, in effect, we end up acting a lot like a persistent memory cache once it's been warmed up, right? I mean, you have to warm up memory caches as well, but the warm up is all local with respect to the disk. So yes, we would recommend. I mean, generally speaking, we would recommend using Mongo for this one. But that said, I wouldn't say you should use Mongo for all problems. In fact, there's a subsequent slide where I'm going to suggest using something else. Okay, so product catalogs. By this I mean some sort of web interface type. Conceptually anyway, an e-commerce site where you go and you look at shoes or something. There's shoes being served out of MongoDB. Product catalogs are kind of a nice use case for Mongo, at least for the data model purpose, because product catalog information tends to be relatively complicated. You might have lots of different kinds of fields, lots of different kinds of attributes. You might store lots of interesting information about the product. Typically, that kind of data is relatively non-volatile. Brand names pretty much can't change because the whole point of a brand name is to be a brand. Product names seldom change, that sort of thing. So it's a kind of interesting sort of use case. You'll often see people using MongoDB for product catalogs precisely because different products over different product types had different attributes. I I bicycle a lot, and I buy things from bicycle websites, and some bicycle websites sell clothes, and clothes have sizes. I suppose bicycles have sizes, but different things in their product catalog don't have sizes, like tire pumps. I guess they might have sizes too. And I'm sure there's something that doesn't have a size. What's that?
Bike lights.
Bike lights. Yeah, sure, bike lights don't have sizes. So there's different kinds of attributes. You might store some attributes for certain purposes and some attributes for other purposes. There might be attributes that you search on and attributes that you don't search on. For example, you maybe don't care about searching on colors of things. So if somebody searches for bicycles, you might show them bicycles based on sizing, but not on colors, at least for search purposes. So there's a lot of interesting kinds of reasons why people would use MongoDB and its document structure for storing catalog information. But that said, there are some sort of interesting kinds of limitations. So for one thing, let's say you have lots of different kinds of, actually this slide is kind of spanning pattern and anti-pattern, I apologize. Let's say you have lots of different kinds of products, like fundamentally different kinds of products. Bicycles and also hams. Because you're some sort of gigantic website or something, some sort of gigantic vendor. The set of attributes that is shared by everything is going to be very small, right? And for this sort of application, I'm conceiving of products as being kind of the relatively slowly changing data about products. So probably not things like pricing. And even pricing might be difficult to describe in a generic sort of list. Anyway, if you put all of your products into one kind of collection, then because different products will have very different kinds of attributes, it would be difficult to build indexes that can be very useful for all of your products, right? So MongoDB at the moment, and probably for the foreseeable or possibly conceivable future, is going to have a limit on the number of indexes you can have on a collection. If you're some gigantic e-commerce site with every kind of product under the sun, the set of attributes that is shared by all the products being basically nil, would mean that if you wanted to index on any particular attribute, that index would only be useful for a very small subset of your product types. So, salty doesn't apply to bike lights, and I don't know, some other interesting attribute probably doesn't apply to hams. So one possibility would be to think up some very sort of, possibly very coarse-grained, possibly more fine-grained hierarchy of different sorts of things, food versus sporting goods, that you would put into different collections based on how you could index, how you could take advantage of indexing. Because there's not a lot of point to building an index on such different kinds of things that most of that index will basically just be null values. Does this point make sense to people? It's a little bit of an implementation detail, but it's also sort of, a pattern. And I've seen people try the use one collection for everything under the sun, and indexing, that sort of thing is very, very hard to do effectively. Now, one interesting kind of example of an anti-pattern that I was just inspired by a recent customer visit had to do with different kinds of work, data that they were co-locating that they probably shouldn't have. So in their case, basically the point is, remember to design for what your application actually needs to see. So in their case, they had localization information. So they had product catalog that represented products, and there were translations of information into different languages. And they were putting all of their translations into the same document. So if I went and looked up my shoe, conceptually speaking, when they went to look up my shoe, they would get the English and the French and the Dutch and the German, whatever. But the interesting thing is, they were never displaying more than one language's worth of data at a time. And so what were they getting in exchange for this? They were putting all the localization into one document, but they were only showing one language at a time. Well, what they were basically paying was an awful lot of overhead to pull one document out that was probably conceptually 10 or 50 times bigger than what they were actually looking for any particular query, and then serving back just one language's worth. And now, to get into some implementation details I mentioned earlier, MongoDB uses memory mapped files in a fairly direct or straightforward way. So if you have a document that contains 50 languages worth of translations of product metadata, that document might be a megabyte in size. If you're interested in serving back only, whatever a 50th of a megabyte is, a few tens of K, you will, in general, be accessing quite a large chunk of that document, because the documents are also serialized in some kind of order, and if you're interested in finding some random language that might be in the middle of that document, we might need to read in, the server might need to read in 500K worth of data in order to get you your Catalan translation of the shoe metadata. And so the point of this example is that's a kind of unnecessary, conceptually speaking, you can think of it as a normalization, or you can think of it as a denormalization. It gets a little hard to think about. Putting all that data into one document might seem like it's more organized. On the other hand, you're never interested, or almost never interested, in seeing more than one language's worth of data at a time. So splitting that sort of data up into separate documents would be strongly recommended. That's what I told these users. Now, having said all of this, at some point you're going to, if you're a completely totally generic e-commerce site with all kinds of different products, at some point you'll probably outstrip what MongoDB can actually do in terms of semantic type queries or conceptually complicated type queries. It's actually not, there's a sort of hard to characterize distinction between query and search, right? Query in MongoDB is based on fields that ideally are backed up by indexes, and you say, I want those documents where these fields have these sorts of values. But that's very different from sort of different kinds of searches, like full text searches or graph searches. And so we actually have a number of customers who are doing things where they need search facilities that go beyond what MongoDB currently and perhaps for the foreseeable future provide. So for example, full text type search. Or in other cases, especially with social networks, which I'll get back to in the next slide, graph type search. Who are all of the people that are friends of friends of friends of so-and-so? Those sorts of search functionality are well implemented by some other systems. In the case of full text, something like Solr or Sphinx does full text pretty well, and we have a number of users who are using MongoDB as a hybrid approach with some external indexing system like Sphinx or whatever. And this works, as well as it works. And it's not an unreasonable approach if you need to do some more complicated kind of search than MongoDB currently provides. The one thing I would caution you about is that if you're using some external index for, graph analyses or something like that, and your query against the index is supposed to give you back a bunch of primary keys that you'll then go look up in MongoDB, you should be careful to note that very long inquiries are expensive to process. And this is not specific to MongoDB, this is just sort of the way that things work. Our indexes are designed for ranges. In principle, we could have indexes that would be better designed for purely random access, but in any case, if you're looking up totally random primary keys out of a total data set, if there's no locality of any sort, you're going to probably experience some paging and some overhead, just in general, looking up total 500 needles in a haystack of a million things. And I can explain this a little bit more if anybody's interested in this sort of thing and how you could avoid it, perhaps after the talk, or if anyone has a question at the end. All right, let's talk a little bit about social networks, because that's a thing that a lot of people do with systems like MongoDB. The thing that's usually most interesting or most important about social network type applications is actually the kind of data that's the most volatile. So for example, it might be the friend relationships or the follower relationships, or it might be the queue of posts that I'm supposed to see the next time I log in to the site, or the things that are in my Twitter feed. I'm actually not much of a social network user, so I don't know what the proper names of these things are for the popular networks. One obvious or potentially obvious way of storing this sort of thing is to embed this kind of data into one document. So for example, I might have a user document in some network, and I might have 100 friends, and you might just embed the primary keys of my friends in my document. This is not a very good use of MongoDB. MongoDB's document structure allows you to store rich and complicated kinds of data. The trouble is, if that data is highly volatile, you will often run afoul of moderately obvious and intractable problems in how we actually lay the data out. So if I have 100 friends at this time, and suddenly, or maybe it's followers, because followers are not me changing things, but some other people do. So if I'm tweeting and 1,000 new people want to follow my tweets, suddenly, if you're embedding the followers in the document representing me, suddenly my document has to be extended quite a bit. Now, there are some heuristics in the database for trying to make some extra room for documents to grow, but any particular highly volatile growth pattern will totally bust the heuristics that we have. And so very frequently growing documents is a kind of MongoDB anti-pattern, a pretty serious one. And there's, I mean, I don't know of any system that's really great at this. If your records if your varchar fields, I suppose, in a relational database are very rapidly growing, you're going to have, over all of your documents, you're going to have some performance problems there as well. For MongoDB, the best recommendation is actually to be a little bit more relational and to represent friend or follower relationships as a separate collection, representing, with a follower and a followee or something like that. So it would be just sort of like a linking table in a relational database. And then adding or removing followers would be inserting or removing individual documents. And you could index that such a relationship on either of the fields. So, I mean, this is actually kind of a relatively prominent anti-pattern, which is, it's not specific to social networks, it's just highly volatile, explosively growing documents are a bad pattern for MongoDB. What are some sort of prospective patterns with MongoDB? So social networks actually have this interesting kind of property. Actually, many sites have this kind of property. Product review sites, or really any kind of place where absolute or strong consistency is not required. If you sign in and look at my LinkedIn page or something like that, it kind of doesn't matter whether you're seeing the absolute most up-to-date representation of my LinkedIn profile, because you'll never know. If you happen to hit my LinkedIn page and it turns out that you're seeing data that's 5 seconds old, I just added some new contact, and you don't see that new contact, it's not going to matter to you very much. Unless it so happens that for whatever reason you're a friend of that contact and you just said, oh, well, I'm now linked to Richard Kreuter. The general point is that most of the time, if you see the results of what are usually called eventual consistency in a display of sort of this kind in this sort of application, the typical user will not notice. And so the business requirements and the user experience are completely insensitive to the functionality of eventual consistency, and you can get eventual consistency out of MongoDB by performing what are called slave OK reads. That is to say, in a replicating MongoDB deployment, you can either read from the writable node, which is usually called the primary, or you can read from the read-only asynchronously replicating secondary nodes. If you read off a secondary node, there's a chance that you'll get data that is, generally speaking, not more than a few seconds behind the data that's on the primary, but it might be as much as a few seconds, or under unusual circumstances, maybe minutes, or if something's broken, it could even be hours, though. In that case, you should probably turn that node off. But if you're reading data that's a few seconds old, and you're a system that is tolerant of that sort of thing, either for business requirement purposes or for user experience purposes, you can get a lot of read scaling. And so that's a pretty common use case for why you would do slave OK reads in MongoDB, which is basically the interface to eventual consistency. Now, there are features or places that, of course, need strong consistency, and the default behavior of MongoDB is to perform reads only against the writable primary server. And so in that case, you'll read back anything that was written. And so in that sense, you'll have strong consistency. And even in social networks, there are such pieces of information. So for instance, the relationship status. If you get that wrong, you will probably offend someone significant other. So be careful with that. That one actually happened. Pretty bad. Okay. So now I'm going to move on to something that's technically orthogonal to, by the way, I was not told how long to speak for. It looks like I've been going so far for just under 45 minutes. I only have a couple more slides, so if you're tired of hearing my voice, don't fret. So now I want to move to something that's a little bit orthogonal to application spaces and just talk about architectural things. So in a service-oriented architecture where you have totally decoupled modules that, or at least conceptually they're supposed to be decoupled modules that are somehow strung together by, I don't know, some third party. If different modules don't actually need to talk to the same data, which is not too unusual actually, there's no organizational advantage in MongoDB to putting different kinds of data in the same deployment. Now what I mean by that is we don't have multi-document or multi-record, so to speak, transactions. The unit of granularity on write operations is the individual document. And so you can't do a transaction across 2 collections or across 2 documents in the same collection. And so to a pretty good approximation, if you have 2 different modules, A and B, and they're reading and writing from different collections, it's really just a matter of taste, whether you put those collections in the same server or in different servers, or thinking bigger in one cluster or in another cluster. And there might be a little bit of overhead managing different kinds of connections. This module talks to this database, this module talks to that database. But some of the reasons why you have to co-locate data in one place in a relational database have to do with transactions across tables. None of that applies in MongoDB. So if you have different pieces with different workloads, this one's extremely write-heavy. You might put that into a sharded deployment with lots of pieces. This one is, maybe less write-heavy, or it's write-heavy, but it's only manipulating a small amount of data. That could go into a different, hopefully replicated deployment, put on different boxes, that sort of thing. And so you have a lot of flexibility in these very decoupled systems about how you might deploy MongoDB. All right, now I just want to say something about operational things. Monitor your deployment. This is a pattern. Seriously. We, 10gen, have recently made available as a free service to anybody who wants to use it, the Mongo monitoring system. I can talk to you about it in more detail offline if you're interested. Basically, you just install a small Python program, and it uploads server statistics, totally anonymized server statistics that say things like how many inserts were done on this server over the last minute, for the purpose of generating things like charts and graphs and even alerts if you enable that functionality, so you can get an email when pieces are down. It is absolutely vital for you to see measurements of your MongoDB deployment, and not just at an individual moment in time, but across time. That's what the graphing is for. So that you can see, oh hey, this is my memory usage, and it's going up. Oh, wait, I only have so much memory on this system. You need to be able to see that stuff. And an operations anti-pattern is not monitoring, really. This happens too. I cannot stress this enough if you're more of an operations person than an application design type person. This is really vital. I know that people are laughing because this is probably obvious to those who've been in trenches, but seriously. Okay. What?
Maybe we're laughing because we're actually committing that.
Yeah, sure. Okay. One other thing that is worth mentioning, and I can actually just tell you, I was just having a conversation with one of my colleagues in New York. I work out of the New York office. Our New York office, we're at the point where we might start using bathrooms for phone calls because we're just out of space because we're growing so quickly. We've failed at this pattern. You should add capacity before you need it. So conceptually speaking, what does this actually mean? To a pretty good approximation, most databases, most MongoDB databases and other databases, there's some sort of locality of data access, and so there's something that you can call a working set, which represents what you're accessing most of the time. Provided that for a single MongoDB process, a single Mongo server process, the working set is not bigger than your physical memory space, you're not at capacity. Once you're getting close to your physical memory limits, or that is to say the resident size of your MongoDB process, for those of you who are sort of gearheads, once the resident size of your MongoDB process starts approaching the physical memory size, you're getting close to capacity. Once you're close to capacity, it's actually a little late to start adding capacity. So here's why. Let's say you're deploying a single non-sharded replica set. Again, for people who don't know our sharding architecture, the point of sharding is to keep the data approximately evenly balanced across however many roughly equivalently sized, ideally equivalently sized shards of MongoDB servers. If you have a single replica set, so some number of copies of the data, and you add another, you go from one shard to two shards, how much data has to move to balance things out?
Roughly at least half.
About half your data, right? So presumably, if your database is like most databases, only a small amount of your data is actually being accessed at any particular time, and so you'll have a lot of stuff on disk that you're not accessing very much. But in order to move that stuff to a new shard, we have to page whatever it is that we're moving to another shard, basically through memory, so to speak, to transmit it over. And so the net effect of this is, let's say you have a 500 gigabyte database, you're maybe only regularly accessing 15 gigabytes worth of hot data. Once you add that second shard, 250 gigabytes have to move over. And for that duration, there's going to be contention between the stuff that's being migrated, or sorry, the operation of migrating that data is going to contend to a certain extent with your operational capacity on that individual shard. I'll get back to you in a second. Additionally, we intentionally keep the migration process relatively slow. So in our case, 250 gigabytes of data, that could take, I don't know, 24 to 48 hours to balance out. So the balancing there, that now everything will be operational during that balancing phase, but that balancing will take you quite a while. So when once you've actually reached capacity, it's a little bit late to then, I mean, you can do it, but it's not going to help you for, maybe days. You have a question?
Is that what happened to Foursquare?
Everything that I'm allowed to say about Foursquare has been said online, so I encourage you to Google. I know some things that I'm not allowed to say, and I'm not going to say them, and especially with the camera on me. And so anything that you want to know about Foursquare that I'm allowed to let you know about Foursquare, you can find. Question?
You say when your working set approaches the size of your memory.
Yeah.
Shouldn't that actually be your working set approaches roughly half the size of your memory because of disk caching and other things going on in the operating system?
Well, okay, so the question is, shouldn't I be saying working set being half the size of memory? Actually, no, at least not on Linux. Linux is not going to, generally, if you have a memory mapped file, that's going to count as part of buffer cache, but it's also going to count as part of residence size. So it's not going to, the buffer cache is not going to interfere with the count for memory mapped files. So basically, when you mmap, 500 gigabytes of files, the operating system says, sure, on a 64-bit platform, of course, the operating system says, sure, you have 500 gigabytes of files mmap, but only so much of that is going to be able to be paged in. Mm-hmm. And that's going to be the resident cost. And the buffer cache, in that case, so of course, ideally, you would only be running only one sort of MongoDB process on such a box, and not any other thing that's memory intensive on the same host. So. All right, I think I have maybe one or two slides remaining. Right, yes, this is a thing that I almost alluded to just now. An operational anti-pattern is co-locating MongoDB processes in a cluster without any kind of justification or without needing to. What do I mean by co-locating? In a MongoDB cluster, a sharded cluster, well, each shard has to have at least one process. Ideally, there would be 3, and you might have n shards, so now you have 3 n processes. There need to be 3 configuration servers that handle metadata for the sharded cluster, so now you have 3 times n plus 1 processes. Plus you have some query routers called MongoS's. You could have arbitrarily many of them. So you have, quite a number of processes. If you put them all on the same host, you're putting eggs in one basket. Now, under certain circumstances, this might make sense. There are different kinds of failure scenarios where you would have degraded operation, but no loss of availability. But generally speaking, the more things you put in one place, obviously, if that place ceases to exist, there goes your fault tolerance. So this gets particularly complicated or hard to think about if you're thinking about the cloud, because you really don't know what's going on here. So yeah, don't co-locate things on cloud servers, really ever. Yeah.
Also, with regards to your replica sets, there's been some discussion amongst my coworkers and I about doing 2 full replica set members and 1 arbitrator, or would you recommend doing at least 3 full replica set members? Okay, so the question is, in a replica set, which for people who aren't familiar with this, a replica set is some number of processes that all of the ones that store data have copies of each other's data. You can have a member called an arbiter that doesn't store any data, but that counts as a member of the set for determining things like majorities and quorums. So should you have, is it okay to have 2 members that store data and 1 member that's an arbiter just for sort of head counting purposes? And the answer is yeah, that's fine. The reason that we have arbiter processes is to reduce the cost of deploying a replica set. If you only want to pay for 2 data storing nodes, you can put an arbiter on some lightweight box or even in principle on a cloud box. I understand it's okay. I mean, obviously you wouldn't provide the arbiter if that wasn't okay.
Yeah.
I'm just saying, in terms of as you scale up, pattern versus anti-pattern.
Sure. So you're basically asking how many copies of the data do you need?
As you scale up, is it at what point does it make more sense to drop the arbiter and have a 3rd full replica set member?
It depends entirely on the requirements for the application. So for instance, I mentioned before that some applications can take advantage of eventual consistency by means of slave OK reads, and other applications can't. If your application has no capacity to take advantage of slave OK reads, then extra copies of the data are only valuable for things like disaster recovery. Your application can't read from them, so you're not going to get any extra read throughput out of extra secondaries. But you might have extra secondaries so that you might have 2 in your primary data center and 1 in your disaster recovery data center. I apologize for people who don't know our architecture. A secondary is a read-only copy of the data. It's a replica set member that at that particular point in time has the role that it is read-only. So it's a copy of all your data, but you can't perform writes against it. So you would have a primary node that you could do writes to, and a couple of other nodes at this point, at that particular moment in time called secondaries that maintain copies of the primary's data but can't be written to. And then the idea is with replica sets, you have automatic failover so that if the primary fails, one of these other secondaries will take over the job of being primary and accept the writes. And then you would presumably go and fix the primary that failed. So to answer your question, it depends a lot on what the application needs to do, what the business requirements are, that sort of thing. If you're not able to take advantage of slave OK reads, then the only real question is how many copies of the data do you need and where do you put them? And if you wanted to have 2 data storing nodes in your primary data center and a 3rd data storing node for disaster recovery purposes in a separate data center, that would probably be a pretty good idea for things like data center failures. But normally you would you would prefer either of the nodes in your principal data center that were closer to your app servers or something like that. But that's a lot of this is actually an economic discussion rather than technical.
And getting back to this handy pattern, co-locating Mongo config processes with the MongoDs or MongoS processes, does that make sense or not?
So in a sharded cluster, we have another kind of process called a config server that stores metadata about where the data is. You can put config servers on the same host as another normal data storing member. What that co-locates is the possibility that both one of your sort of application data members and also the metadata goes down. The failure scenario when a data member goes down is all the application level read and write operations happen, but there's no balancing of data. So in that case, that probably wouldn't be that terrible a situation for a short duration because you might not get too imbalanced in your data sets. But if that were something that you wanted to be able to sustain for an indefinite period of time, that would not be a good idea. Okay. As I said, for those of you who are tired of hearing my voice, I'm almost done. So let me say 1 or 2 things about schema change. Because people often think, well, okay, I can design for Mongo for my application today, but how do I change things tomorrow? In SQL, I can execute alter table statements, and that makes my life happy and